Live from Norwich with the best of the fest, the Naked Scientists.
Hello, Chris Smith and also Helen Scales here with you for our third daily update from the BA Festival of Science here at the University of East Anglia in Norwich. And every evening this week we're here with a best of the fest, a roundup of the highlights of the day. And here's a taste of what's coming up in the next 30 minutes.
Today on The Naked Scientists, I'll be finding out what the younger visitors to the BA like about science.
Doing loads of experiments and things like that. Everything really. Science is fun.
Blowing stuff up.
There's always one. But blowing things up won't be too far away, as Madeline Humphreys from Cambridge University joins us to talk about volcanoes.
We're going to be looking at how we can track the movement of magma as it rises up underneath the volcano.
And with even more explosions, Peter Coles from the University of Nottingham reveals the secrets of the universe.
Tonight I'll be talking about how the Big Bang turned objects which are smaller than the inside of an atom into the largest structures that we see in the universe.
And if we mix big explosions with a day of kids' hands-on science, we get kitchen science, where Derek, Herbert Hupper and James make a lemonade volcano.
Whoa!
I see fizzy stuff all coming out of the bottle.
Stay tuned to find out if anyone got wet.
And after 8 o'clock, we'll be handing you back to Sue for a science phone-in. And if you'd like to talk about any of the items we discuss on tonight's programme, or just ask us any question at all about science, then all you need to do is call us. And the number is 0845 30 50 007. That's 0845 30 50 007.
And don't forget, you can also take a look at the Naked Scientist team on our webcam if you log on to bbc.co.uk/Norfolk and click on webcams, although there are no guarantees exactly what we'll be wearing each evening, so certainly your choice and your risk. Right, yeah, it is the Naked Scientists, Chris and Helen. First up, let's take a look at what's been happening at the conference today. Really exciting, actually. I got talking to a guy from the University of East Anglia, Helen. His name is David Russell, and he's working on nanoparticles. Now, sounds exciting, but also sounds a bit overwhelming. What are nanoparticles? They're really, really tiny things. These things are roughly 1/5,000th the width of a human hair, these tiny particles of gold. And you can link things to them, chemicals, and then use them to track things in the body. And what he's doing is providing the first snapshot of what the chemistry that's going on inside a living cell is actually like. Because the problem with microscopes and things is that if you want to get a good look at what cells look like inside, you have to kill them, because you stick the cell onto a microscope slide and it dies. But this way, you can look at things growing in the Petri dish. You can feed macrophages, white blood cells, which is what he's looking at, bacteria and viruses to eat. And then you can watch how they produce a substance called nitric oxide, which they use to kill bacteria and viruses. And you can watch how they make that stuff in real time. And it gives you an idea as to how the immune system works.
So how is he actually using them to look at? Was that what kind of imaging was? Is this the gold particles itself that he's looking at? What
happens is that you link to the gold particle a special protein, which, when those gold particles get inside the cell, which they do completely harmlessly, when the bacterium is eaten by the macrophage, the macrophage starts to produce a substance, nitric oxide, and the nitric oxide locks onto the gold nanoparticle and makes it glow. And it gives out light, and so you can see exactly where in the cell this chemistry is going on, and you can also measure directly how much of it there is, because the lighter it is, the brighter it is, the more nitric oxide there must be.
And was there anything in particular he talked about he's already discovered, or is this all still in development, just as a technique?
No one in the world is doing this. This is the first time it's ever been done, and it's a first for not just Norfolk, but also for the UK, of course, so that's very exciting. But also, this may have applications in cancer, because these nanoparticles are hungrily devoured by cancers. And what you can do is link to the nanoparticles another substance which makes them mop up light at the red end of the spectrum. So say you've got a cancer, and say it's in the lung or the gut, you feed the patient some of these nanoparticles, and obviously this is not in clinical trials yet, this is what they think they're going to be doing. You feed the patient some of these nanoparticles, the cancer picks them up far more than healthy tissue in the rest of the body, and then you could put a telescope into the affected bit of tissue and shine red light of the right wavelength at the nanoparticles, which are now all inside the cancer, and as soon as red light hits them, what they do is activate a certain form of oxygen that's in the cells. There's oxygen everywhere in the body for obvious reasons, but these nanoparticles convert the oxygen to a very reactive form, which is highly toxic. And because only the cancer has got it in, just the cancer gets affected. So it's a very good way to sort of create a magic bullet, to target the therapy just to one part of the body, where the cancer is just to the cells or the part of the body that needs the therapy, and that minimises side effects.
All sounds very space age to me. Well, after the session I went to this afternoon, the big question on my mind is, should I eat fish? And I also found out a rather surprising link between healthy, smiley Eskimos and omega-3 fatty acids. Now, Chris, what do you think? Do you think you should eat fish? Do you eat fish?
I do, actually, and the thing is, I have a little bit of inside information on this because we were talking to Nick Wareham last night, and the one thing he was talking about was a study that a friend of his is doing in Alaska, looking at how much Eskimos move, because exercise is very important in terms of how healthy you are. And they said that their study was a bit frustrated by the fact that when these Eskimos are given pedometers to measure how many steps and how far they're walking, when they go out on their skidoo, it bumps around all over the snow, and it looks like they're actually running a marathon every day, but in fact they're not, of course. They're just going out on their skidoo. But they eat an enormous amount of oily fish, and they also eat a lot of fat in their diet, but they're very, very healthy.
Yeah, and that's exactly it. I never really thought about making this link, but actually that was what first sparked off scientists thinking about why a fishy diet might be really good for us, because these Eskimos, these Inuits, do have a very fishy-based diet. They don't eat much fresh fruit and vegetables, the sort of thing we might think would make us healthy. And there are other populations in the world. Do you know who some of the longest-lived people in the world are? What countries they might come from?
I'm tempted to say Japan, actually.
You're right, actually, yes. Japan and also Iceland. And again, their populations
fish dominated.
Fish.
Yep.
And so we've heard a lot about omega-3 fatty acids. And what the session I went to this afternoon was a panel of 4 experts basically arguing various things for and against why we should eat fish. So we had food researchers, we had some environmental and social scientists telling us about the social and environmental impacts of catching fish. But I think some of the pros and cons of, are fish good and bad for us, were very interesting. I mean, we hear about omega-3s, and that's something that oily fish have, and it's all about that ratio in your diet between that and other types of fish, and how we can maybe improve that. But I think very also nice to pull out the fact that there are some fish that are very bad for us. You know, which the fish that's
puffer
probably...
fish is not good, is it?
Puffer fish, the fugu, yes. Yeah. Cook that wrong and you're out there. So I think before and after the discussion, we had to put up our hand to say whether we would eat fish or not, and it didn't really change. I think we all have to just take all these arguments on board. There's very, very difficult to decide here or there, but I think some fish is definitely good for us.
The bottom line is omega-3 fatty acids thin your blood, they reduce the risk of heart disease, and therefore they're probably a good thing, but don't decimate the oceans at the same time.
Yes, don't decimate the oceans. I mean, we talked about the links to bowel cancer as well, which are really quite encouraging too, so lots of good reasons, but where can we get it from, I think, is the question.
Tis the Naked Scientists, Chris and Helen, and if you want to ask us any questions after the 8 o'clock news, we'll be here with our guests. We have Peter Coles and also Madeline Humphreys, and we're going to talk about the Big Bang and volcanoes in a second. Any questions? 0845 30 50 007. Now, to give you a taste of what it's like on the ground at a festival like this, we're of course at the BA Festival of Science this week. Our Naked Scientist reporter Anna Lacey has been out and about, and so far she's brought us the lowdown on climate change, told us how to spot what politicians are telling porkies, and today she's been out to find out what's turning kids onto science.
Well, I just really like science and it's really fun, so...
It is really fun, it's going to be a really good day.
Yeah, I'm looking forward to doing the slime.
Doing the slime? What's the slime all about?
We get to make slime, and we've made hovercrafts today already.
Yeah, they were really good.
Well, with such tempting science action afoot, I figured I'd check out what else I could get my hands on. I spoke with Claire and Emma from Noisemakers, and Claire told me what the kids, can do with the robots on their stand.
They can come along and they can actually program the robot, and they can run the robots around the pen, or they can move the remote control robot around with themselves, so it's quite interactive. They can come and sort of get some hands on.
Well, also on this Noisemakers stand, we've got some amazing kind of bubbling liquid, bit of foam and steam, and Emma, you're here demonstrating this. What's it all about?
Well, I try and bring bubbling, foaming, interesting reactions in to get the kids just pulled into the idea of doing chemistry, because that's the bit that fascinates everyone. The idea is to link it up with catalytic converters and show them how catalysts work.
So how does a catalytic converter work?
You've got little tiny particles of metal which are the catalyst, and you get gases which come out of the engine which are bad for you. They get grabbed by these little particles of metal, and a chemical reaction happens which turns them into gases that you can breathe, like nitrogen and carbon dioxide. Once the kids start to understand that by doing chemistry you can actually make a contribution to the environment, they start to get a lot more interested.
But it's not just about slime, chemistry and robotics. There are a number of experiments teaching children about the human body, the environment, and how the Norwich canary can help demonstrate genetics. Kathy Morn from the Norwich Castle Museum talked me through some of the specimens.
Well, we've got one sort of standard canary, and we've got one canary with a very strange hairdo, I suppose you'd describe it as, or a mullet with a sort of feather plume at the top. And what we're hoping to do is look at the genetics and the selective breeding. It's a bit more of an interesting example than just looking at cats and dogs.
Whoever decided that a mullet looked good on a canary?
I've no idea. I'm sure it's one of those chance things.
My next move was to Hollywood, where rough scientist Jonathan Hare from Suffolk University told me whether those famous action film moments are science fact or just plain movie magic.
There's the famous film Die Hard, where Bruce Willis is at the top of the Nagatoni Tower. And to escape from the baddies in the film, he ties a fire hose around his waist and jumps off. And, of course, he's brought to a standstill 20 metres below and he shoots his way in. And the question is, could you do that, or would it just cut you in half?
And what's the quick answer, yes or no? Could he do it?
Well, Robert Llewellyn, who I did the series with, likes to think there would be Bruce and there'd be Willis.
Ouch. So what did the audience think? I asked Hannah from Norwich why Hollywood science was such a hit.
Fun and exciting experiments or different ways, looking at science in a different way rather than just the boring textbook kind of science that you get at school.
So in short, there are tons of things for young people to get involved in here at the BA, and the events run until Friday in venues throughout Norwich. But after a day full of slime, robots and canaries with mullets, the last word has to come from the kids. Do you like science?
Yeah!
Sounds fun. Thank you very much to our Naked Scientist reporter, Anna Lacey. She'll be back tomorrow with a bit more Best of the Fest. Now, this evening, we are, of course, joined by two fantastic guests. Madeline Humphreys from the University of Cambridge, who'll be talking to us in a few seconds about how volcanoes work. But before then, Peter Coles is here from the University of Nottingham. Hello, Peter.
Hello.
Thank you for coming in. And you're going to give us answer to life, the universe and everything. Or at least just tell us about the Big Bang.
Well, I'm not sure I can give very definitive answers about all of the questions of life, the universe, and everything. But in my talk, I was really trying to concentrate on issues that are open and people are really working on now. So that's the focus was more on open questions rather than sort of laying down the law about the way the universe works.
How do we believe the universe came into existence in the first place?
Well, the standard theory now is, of course, called the Big Bang, but I think people don't really understand. They've heard the words a lot, but they don't necessarily know what they mean. The Big Bang is a description not just of material in the universe, but of the entire universe as a system. So it includes not just matter and energy, but also space and time itself. The Big Bang...
Roughly how long ago was it?
About 14 billion years in the past. That's what we think is the best estimate based on the latest observations. So the point is that there actually it wasn't just that an explosion like explosions that we're familiar with that happen somewhere in space. It's an explosion that resulted in the creation of space itself. So there is no
this known universe, I guess.
Yeah.
Depending upon whether we believe in multiple universes or not.
Yeah, well, that's an interesting problem with language, you see, because the universe is by definition everything that exists. So there can't be more than one of it.
Sort of sub-universes and things like that.
There could, of course, we might live in a little bubble, and there'd be other bubbles that comprise the universe, and it might be impossible for us to communicate with these other bubbles.
So can you give us a sort of timeline, a sort of snapshot, if you can manage about 14 billion years in roughly 14 seconds, probably quite tough, but can you give us a sort of timeline for the unfolding of the universe and how we arrive at our present situation today?
Well, I think the best way to think about cosmology is actually to go backwards in time. So just think about what the universe is like now. It's actually very big, very empty, and very cold. There's very little matter in the universe if you average it out. It's about 1 atom per cubic meter, which is a very good vacuum. There's hardly anything. That cubic meter will also contain something like 10 billion photons. But they're very low-energy photons. And
this is just light, photons of light.
Yeah, it's actually microwaves because they're such weak form of light. So the average temperature of the universe is about 3 degrees above absolute zero. It's very sparse and very quiet, and it's expanding.
And you mentioned the microwaves, because they're actually what gives us a clue as to the Big Bang, because there's this background microwave radiation.
Yes, it's the most... It's the largest reservoir of energy in the universe, but it's in a fairly useless form. It's very low-energy radiation.
Why, given that the Big Bang happened 14.8 billion years ago, are these microwaves still hovering around Earth today for us to detect?
Well, the thing is that they weren't microwaves when they were first produced. If we turn the clock back on this very cold, empty universe, it gets denser and denser and hotter, and eventually you reach a time when the whole universe had a temperature of several thousand degrees, at which point it's like the surface of the sun, and the radiation that we see travelling to us across most of the age of the universe, it was emitted when the whole universe basically behaved like the surface layers of the sun.
How do we know it's expanding in the way you mentioned?
Well, that's an observation. It's a mixture of observation and interpretation that gives that. I mean, Edwin Hubble was credited with discovering the expansion of the universe because he observed galaxies and found that they were all apparently moving away from our own galaxy, the Milky Way. Hubble, however, never claimed that the universe was expanding. He didn't really know what was going on. He just saw this kind of strange pattern in the way that the galaxies were moving. And so there's the theorists, but you used Einstein's theory of general relativity and came up with the interpretation that it's actually not so much things moving through space, but the entire space itself expanding and carrying galaxies along with it.
Peter, I've got an email here from John, I think his name's Berger. He's in Canada, actually, and he says the current view of the universe holds that it's expanding to give the impression that the universe is getting larger. So is the space between the sun and the earth also expanding, and therefore could it eventually be used to compensate against global warming?
Well, the answer is that cosmological expansion won't do anything like that. Our galaxy, we're not expanding.
So our solar system's not getting bigger?
No. The thing is that if you think of a system like a galaxy or a solar system, it's kind of collapsed under its own gravity, its own local gravitational influence, and is no longer participating in the global expansion of the universe. So even a galaxy like our Milky Way is not expanding, but the space between galaxies is expanding. So, we expand a little bit as we get into middle age, of course, but our solar system probably won't expand like the rest of the universe. However, it's not obvious. Actually, people look at the stability of the solar system, and it's not obvious that the Earth's orbit will stay exactly where it is relative to the Sun due to a number of other things. So it is possible that the Earth might cool off.
That's Peter Coles from the University of Nottingham. 1,000 unanswered questions there, or 1,000 questions you could ring in with and ask. If you want to ask Peter anything, 0845 30 50 007. From the University of Cambridge, Madeline Humphreys. Hi, Madeline.
Hi.
You've had a lot of press attention today because you published a big groundbreaking paper in the famous journal Nature. What's it all about?
Yeah, that's right. Well, basically, for the first time, really, we've been able to accurately track the physical conditions of the magma as it's moving up underneath a volcano. And what we've been able to show is that as the magma moves up, it crystallises as it goes, and it also heats up, and that's due to the release of latent heat of crystallisation as the crystals form.
What does this tell us about the actual understanding or how volcanoes work in the first place? Because obviously you found this new finding, but what did we think before? How does this change knowledge?
Well, in recent years, people have started to realise that sometimes the driving force for crystallisation of a magma is loss of pressure rather than cooling, which has been the traditional view. And the reason is because when you have a magma at pressure, say you've got a packet of magma that is about 6 or 7 kilometres beneath a volcano, you can dissolve quite a lot of water into the magma. As you rise up towards the surface, the solubility of water decreases, and that means that it starts to crystallise. Basically, as if you have water dissolved in the magma, the most stable arrangement of the molecules is quite loose, it's quite a random arrangement. If you remove the water from the melt, then the most stable arrangement is much more ordered, and so you start to form crystals.
So the volcanoes are making their own heat?
Yeah, exactly. And this is quite exciting because it could mean that it's a new trigger for an eruption. So you could have an eruption that's actually triggered by the magma heating itself up rather than needing an external source of heat.
So which volcanoes have you been looking at to find this out?
We've been looking at 2 volcanoes. The first is Mount St. Helens in the US, and also a volcano called Shiveluch, which is in Kamchatka in Siberia.
Are these by any means typical of your average explosive volcano, or do you think they're special cases and what you found just relates to those particular mountains, and if you went and looked at another volcano you get a totally different story?
Well, first question, I mean, are they typical? They're typical of a certain type of volcano. They're not the most explosive we can get. That's probably something like Yellowstone. But they're also not like volcanoes like Hawaii, where the magma is very, very runny. So they're sort of intermediate explosivity. But the exciting thing about the research is that what we can do now is take what we've found, take it to other volcanoes, preferably ones that have a really good record of monitoring the volcano, and then try and see what we can discover.
How good are we at actually predicting when a volcano is going to go off? Because a lot of people tried to press you today to say, can you, with this, forecast when the next eruption is going to be?
Yeah, they sort of phrase the question in many different ways.
About 15 different ways to try and make someone eventually say, oh, yes, this could be used to forecast.
Yeah, at the end of the day, we're not in a position yet to predict eruptions. But what we can say is, so in order to predict an eruption, what we need to do is be able to take the monitoring data. So, for example, information about earthquakes, which are related to the movement of magma, or information about gas that's released at the surface. We can monitor those sorts of things in real time. What we'd need to do in order to predict an eruption would be take that information and be able to relate it directly to what's happening under the volcano. And I think this is certainly a step towards that.
That's Madeline Humphreys from Cambridge University, and if you'd like to ask her anything about volcanology, the phone number 0845 30 50 007. She'll be here after the 8 o'clock news to talk about that. And of course, we're here, Helen and I, to take any science questions on anything. If you have any general questions that you'd like to ask us, same number, 0845 30 50 007, and Petro is collecting calls as we speak. Well, it's time now for the third of our special kitchen science experiments. Every night this week, our kitchen science team will be paying a visit to a different kitchen around the region, and tonight, kitchen scientist Derek Thorne is with Herbert Huppert and James from Cambridge to show you how to demonstrate for yourself exactly what Madeline was just talking about.
Hello there, and today we've come to Cambridge University. We're actually in the Department of Applied Mathematics and Theoretical Physics, and we've actually got an experiment lined up which you can do at home, so listen out for the details. And with me to describe it is Professor Herbert Huppert of the university. So what have we got lined up today, Herbert?
Well, what we're going to be doing is investigating some of the important ingredients in explosive volcanic eruptions.
Fantastic. And also, even more importantly perhaps, a fantastic helper who's here. So could you please tell us your name and age, please?
My name is James and my age is 10.
Thank you very much indeed, and it's great to have you here, and you're going to be doing our experiment today as well. Now then, you at home, this is a spectacular and very easy experiment, and all you need is the following, OK? You need a freshly unopened bottle of some kind of fizzy drink. Lemonade, Coke, whatever, that's fine. 2 litres preferably in a nice, simple, circular bottle, OK? You also need some mint Imperials, and, if you've got it, a Smarties tube. Now, if you don't have mint Imperials or a Smarties tube, then you can just use some sugar, all right? So I'm betting that most of you at home have got some of these things, right? But we're going to hear about what to do with those in a moment. The only other important point is to do this in the sink, and believe me, you'll find out why. Anyway, Herbert is here to tell us what to do with all these things and to tell James how to do it. So, Herbert, what do we do?
Well, James, take the Smarties packet, and you've emptied it of all the Smarties, and you've also cut one top off, so you have a long tube that's open at one end. Then you take the packet of Imperial Mints, open it, and then pour as many Imperial Mints as you can into the Smarties tube.
And maybe tell us how many you're getting in there as well. All right, I think that's about full. How many do you think that is?
13.
OK, well, we've got something like 13 Imperial Mints there. What's next?
Now you bring them over here to the sink, in which you have the lemonade bottle, and you open the lemonade bottle, and it fizzed just a little bit. That's because it has dissolved carbon dioxide. That's to make it taste good, and it comes out of solution.
And so then all you have to do is, using the Smarties tube, you have to get the mint Imperials into the lemonade as rapidly as you can. So that's why we've kind of used this Smarties tube setup. And also do remember that if you don't have mints, then you can also use sugar. The key point is still to get it in there as quickly as you can. So just use a paper funnel or something and get about 2 tablespoonfuls into the lemonade. OK, now I think James is ready with the mints and the lemonade.
And I might just help a little bit by putting my hands around it to make sure the Imperial Mints all go into the lemonade bottle and none end up in your stomach.
So here we go. Herbert's kind of cupped his hands around the top here, but in they go. Tell us what you see, James. Whoa!
I see fizzy stuff all coming out of the bottle.
Yeah, I mean, that was quite something, I must say. And did you actually get all of the mint Imperials in there?
No.
I mean, how many actually went in?
4.
Exactly, and we had 13 in that tube, and all we needed to do was put 4 or 5 in there, and we saw a massive amount of foam. I mean, this thing did not just foam over, this thing actually really, well, exploded all over us, and Herbert is currently drying his hands, because he was bravely cupping his hands around the top of the bottle there to make sure it worked. So, Herbert, I mean, we need to know, firstly, why did this happen?
Well, the mint imperials allowed the carbon dioxide that was dissolved in the lemonade to come out of solution, because there's bits of sugar on it, and that acts as nice areas where the carbon dioxide can come out of solution. It comes out of solution as a gas, and as we all know, gas occupies much, much more space or volume than does the liquid equivalent. So suddenly there was a huge amount of volume in that container, and the only place it could go was out up into the air, about 6 inches, I would say.
OK, then, now, also, we, of course, want to know how this all relates to volcanoes. So how is this kind of similar to some volcanoes?
Well, some volcanoes have liquid rock that have a little bit of water or carbon dioxide or other volatiles, gases like sulfur dioxide, in them, and as they rise up to the surface of the Earth, the decrease in pressure and the fact that there are little crystals in the liquid magma allow the carbon dioxide of the water to come out of solution, and then it's exactly as we saw.
Well, there you go. So that's all for this time, and thanks to James and Herbert as well. And tomorrow there will actually be more science, which you can do at home, so please do listen out. We'll actually be at Billericay School in Essex using a lemonade bottle, again, and also a torch to make a fibre optic cable. So do join us then, and it's goodbye for the moment.
Thank you, Derek. Tomorrow on our Naked Scientist Best of the Fest from the Science Festival of BA at the University of East Anglia, we'll be joined by Crispin Little from the University of Leeds, who'll be talking about deep-sea hydrothermal vents and the evolution of weird and wonderful organisms that live there. And also Paul Morris will be joining us from Portsmouth University. He'll be telling us whether our dogs get jealous when they see you petting your hamster, or does your hamster get the hump when it sees you petting the dog?
Andy in Hertfordshire on the text says, please could you tell me the speed of light? He's put an S there, but I'm sure he means the speed of light. I've asked many people and never got an answer.
Well, I think, let's look at two issues here. There could be a speed of light, but there could also be a speed of sight, because, of course, when light reaches your head, it's got to be processed by your eye, retina, nervous system, and then presented to your consciousness. And what people at Wimbledon know only too well is that tennis players move far faster than actually their brain can process visual information, so they're actually working at a subconscious level when they're hitting shots back. So what I'll do is I'll tell you a bit about the visual system, and then I'll chuck it to Peter to talk about the speed of light. How's that, Peter?
That's fine, yeah.
Okay. Well, when the light comes into your eye, it hits the retina, which is the light-sensitive part of the central nervous system, and there are cells in there which, when light hits them, it causes channels to change their shape on the cell membranes in the retina, and these cells actually become less active when light hits them, and that's how the eye picks up the stimulus, the light stimulus, and it then converts that signal via a series of very long nerve cells which go along the optic nerve to the back of your head and into your brain, and then the brain processes the visual information and mixes the input from each eye together so that that's how you have binocular vision, stereo vision, right eye plus left eye, and then eventually a third of a second roughly after something happens to you, you become fully conscious of it. But vision takes at least, I'd probably say a fifth of a second before you're aware of something actually being present in your visual world. So it's very, very slow sense to arrive at consciousness. But in terms of the speed of light itself, Peter, you'd better take over on this one.
Well, I think the answer will be a bit shorter. The speed of light in empty space is about 300,000 kilometres a second. And that's as a universal constant. The speed of light in different materials can be different from that, but we're talking about empty space, which is where what most of the universe is like. So
scientists have succeeded in slowing light down, though, haven't they?
Yes. Yeah.
So if you pass it through very dense material, you can get light to travel, almost imperceptibly slowly.
Yes. As I say, materials have a property called their refractive index, and that's basically what the light speed, controlled by what the speed of light through the medium is. So you can do a lot of funny things with light inside a medium, but in empty space, it's absolutely constant.
And anyone that was watching our experiment on the telly about a week ago will hopefully have measured the speed of light in their own kitchen using a microwave. And in fact, if you go to bbc.co.uk/lookeast, you can see the action unfolding in front of your eyes, and there's even a hall of fame for people who want to have a go, measure the melt distance of their margarine, and then enter the distances they measure on to our calculator on our website, and it will record it'll calculate and then record the speed of light according to your kitchen. But Sue, anyway, I hope that answers that question.
I believe it does. Well done to you. You're so clever, aren't you? Now then, also Anne in Angers Green, from sort of sight to noses, said, who first found musk and who decided it was good to go in perfume?
Well, the thing about perfumes is that they're volatile substances. They're things which we squeeze out through the skin in sweat, and they give us our own unique flavour. And all animals, as far as we know, have some degree of scent. Even an ant uses scent to identify members of its own colony. Ants have these things called cutaneous hydrocarbons, CHBs, and these substances ooze out of the ant body, and when another ant comes along, it can tell whether it's a member of its own colony or not by brushing its antennae close to the other ant, and it picks up some of these molecules off the surface of the ant's body, and it can sniff and it can recognise friend from foe. And in the same way, every single animal we know uses these kind of scent molecules to play the dating game, the mating game, and also to signal aggression and to say, hey, I'm a very fit mouse, stay away from my territory, because male mice produce lots and lots of substances called pheromones actually in their urine as well as on their skin, and this wards off other mice away from their territory, and us humans are probably the same. So all animals make these things. They're very good at evaporating from skin, getting into the air and travelling to your nose where they're picked up, and then they pass signals to the brain. People discovered that some animals make very, very stinky ones about 100 years ago or so, and Coco Chanel discovered that these things can be put into perfume in her Paris collection, and of course some of the Coco Chanel brands still exist today. As an aside, you can smell a giraffe about 3 miles from if you're downwind of a giraffe, because it produces an extremely musty smell, let's say.
I'll just put a bit more of number 5 on, I think. Now, Jim on the M11 has said, what's the difference between magma and lava?
Oh, Madeline, that's definitely one of yours.
OK, well, we can do that one. Basically, a magma is molten rock, and it can contain melt, which is a volcanic liquid, or crystals, or gas, or all three. And a lava is a magma that's erupted at the surface, so it's quite simple.
How hot is it?
It varies depending on the composition of the lava or magma. So the volcanoes that I've been working on recently are about 800 or 900 degrees centigrade. But if you went to a volcano like Hawaii, which is basaltic, the magma there would be about 1,200 degrees.
And as you go down underground, the temperature must rise quite considerably.
The temperature of the crust would rise considerably, but if you're just looking at the temperature of the magma, that's probably pretty constant, because when it's a liquid, it's not going to get a huge amount hotter than that.
So how much of that stuff is actually quite high up in the crust, and how much of it actually tracks up from very deep in the earth?
Well, actually, that's quite a good question, because what we don't really know is exactly what the structure underneath a volcano is like. So what we think is that there is a series of horizontal layers of magma, and you might have the deepest ones at about 30 kilometres or so. But the work we've been doing is very much based on the upper 5 or 10 kilometres of the crust, and that's where the processes that control certainly explosive eruptions, that's where they're all concentrated.
Because, of course, tomorrow we're going to be talking to Crispin Little from Leeds University. He's going to talk about hydrothermal vents. So presumably if you've got a lot of water on top of the seafloor and then it's going down into a hot spot, is the crust much thinner there then, so it's hotter or something?
Exactly. Yep. So we're at a mid-ocean ridge, you have the crust is pulling apart, so the actual crust is much thinner there.
I think that covers that one, Sue.
Does indeed. We've got a caller on the line now. It's Rod in Thorndon, and I'll open the line and Rod can ask you his question himself. Hello, Rod.
Hello there, Sue.
Hi, you're through to Dr. Chris.
Hello there, Chris.
Hi, Rod.
Hello. Right, what is the biggest risk to humanity, global warming or Yellowstone Park?
Oh, well, let's talk about supervolcanoes. This is definitely an opportunity for Madeline. Madeline, come on.
Yeah, and a very quick one, aside to that. With the melting of the ice caps, the added weight of the water, will that destabilise or stabilise Yellowstone?
Let's do the supervolcano first, right, and then we'll come to that. So Yellowstone Park, Madeline.
OK, well, if we're talking about whether Yellowstone Park or global warming was a greater risk to humanity, certainly in the next 100 years there's probably a much greater chance of global warming happening than of Yellowstone Park erupting. But if there was a big super eruption at Yellowstone, it would certainly be completely catastrophic, at least to a certain amount of the United States.
Give us the sort of anatomy of the Yellowstone sort of supervolcano? Because I don't think half the world, certainly I don't know how big it really is, that volcano sitting under the US.
I mean, basically what we've got is a dormant magma chamber there, and scientists are monitoring it at the moment, and they're noticing that some months it swells slightly, some months it dies back again a bit, but basically they're monitoring it quite closely.
Because if you look at the past history of the Earth, there have been some massive supervolcanoes that have actually refashioned our planet. I mean, think of things like Tambora, which blew up. You get almost a nuclear winter afterwards, don't you? Yeah, so we'd expect it. The immediate effects of a super eruption would certainly affect a large proportion of the United States, for example, but the later effects could easily affect the globe, and in fact we'd expect them to. We'd expect them to affect climate in terms of putting lots of ash into the atmosphere. It could well disrupt things like El Nino, but people are doing research on that at the moment. It's an active research area. OK, let's look at the other questions, which was, can you remind us, please?
Yes, with the melting of the ice caps, would that extra weight from the sea tend to stabilise or destabilise St Helens? Not St Helens, Yellowstone.
Well, let's talk about ice caps first, because let's talk about the North Pole. The thing about the North Pole is that all of that ice is floating. There's no land mass under the North Pole like there is under the South Pole, so all of the weight of the ice is already pressing down on the sea, so that one's less relevant. Antarctica is a different matter. That's all above ground because there's a big land mass under Antarctica, so a lot of that ice is not floating. So if Antarctica melts, in the same way as the Greenland ice sheet, if that ice melts, it all ends up in the sea and sea level will rise. But the fact is, it's all pressing on the planet anyway, so I think it's a very long sort of or big ask to say, if we melt all this, will this make things destabilise enormously and in our lifetimes trigger tectonic events? What do you think, Madeleine? Well, the only thing I would say with that is that there is some evidence that changing sea levels can affect the stability of volcanoes, but we really don't know which way which way the effect would be. We don't know whether it would make them become more stable or more unstable, but again, researchers are looking into this at the moment. Why would it destabilise a volcano? Well, again, we don't really know. It's more relevant for volcanic islands where there's a direct pressure of the water onto the edges of the island. For something like Yellowstone that's in the middle of a continent, I think it would be much less relevant, but it is certainly a factor. Sue?
Right, OK. Well, Rod, has that answered your question?
Yeah, yes, it's, as we say, we don't really know is the answer.
It's under discovery, is that right, Chris?
I think you can say it's under investigation.
Under investigation, all right, OK. Thank you very much then, Rod, thanks for your call.
Cheers, Sue.
OK, and lastly, it says here, Sue, please ask the Big Bang man, does he think we will ever know what happened before the Big Bang, or maybe he has an idea? Hard question, says Stephen Felixstowe. Sorry about that.
Yeah, yes, it is a hard question, I think, basically because it's meaningless. If you talk about before, that implies some notion of what time is, because time is what gives us a chronology of events. And in the Big Bang, time itself was born at the instant of the creation, if you want to use that sort of rather biblical word for it. So space and time came into existence somehow at the Big Bang. So that time didn't exist before the Big Bang. There is nothing before. Actually, nothing. There's no universe before the Big Bang, and therefore there's no time. So the answer is, I think the question is sort of meaningless.
It's amazing, though, that you can put a time on the universe that has existed. You can say, for 14.8 billion years or so, there has been a universe. Prior to that, there wasn't one.
That's right. I mean, there's another possibility, of course. Our universe could be just kind of one bubble, like a bubble in a glass of champagne, and there could be lots of other bubbles being created all the time with their own times, their own clocks that run in them, and the whole universe, this whole collection of bubbles might be eternal and infinite, but we'll never be able to see beyond our own little one. So that's a philosophical speculation and not something we can test using
experiments. Michio Kaku from City University in New York came to Cambridge last year and gave a talk in which he was suggesting that parallel universes are all over the place. There could be one hovering just a couple of centimetres in front of your face. There's another Peter Coles knocking around in there, sort of perhaps presenting a radio programme or perhaps perhaps playing golf or something. You wouldn't really know. And that perhaps that where you have a black hole, at the other end of a black hole you have a white hole, and all the stuff that the black hole's hoovering up is being jetted out into the second universe as a big bang in that universe. It's like an umbilical cord to a new universe somewhere.
Yeah, these are all things that you can actually describe perfectly well with the mathematics and physics that we know. But there's no experimental evidence for any of them, so they're interesting speculations, but nothing more than that, I think.
OK, well, I think that answers the question. I've just got a quick one. What was the first experiment you ever did? Let's ask that to Peter.
Well, I'm hopeless at experiments, and I always was. But I did have a chemistry set, I remember, and the first experiment that I did was to dissolve a beetle in a solution with copper sulfate.
Did it dissolve?
No, but it didn't survive the experience.
Beetle sulfate.
Oh, gosh, I wish I had the Beatles lined up now. I'll get you back. Thank you very much indeed, and I look forward to another natter for tomorrow.
Live from Norwich with the best of the fest, the Naked Scientists.